Hi, welcome to this talk, a journey through the O3DE animation system. My name is Benjamin Jillich and I'm the animation system tech lead and a senior engineer at AWS. And I'll be presenting some of the basic concepts of the emotion effects animation system, go into technical details for some of the used techniques, and use the animation editor to go from simple animation clips to a locomoting character. We'll start with some basics on the emotion effects animation system. We talk about the main concept of it, called anim graphs, build our first small anim graph and get a character walking. We'll talk about syncing animations and how we can use blend spaces to take our character to the next step towards locomotion. We'll do a quick excursus on motion extraction. And lastly, we'll use script canvas to connect the gamepad and get our character moving around the level. So, what is an animation system? Animation systems are mostly used to animate characters, animals and creatures in games or simulations. The goal is to provide all functionality needed to create a controllable character that behaves as expected, based on either player or AI input. Emotion effects is a skeletal animation system. Skeletal animation is a technique in which a character is represented in two parts, a skeleton and a mesh. Animations drive the joints and thus animate the skeleton of our character, and the skeleton deforms the mesh. We'll use individual animation clips and blend between them in the right timings to seamlessly create a controllable character. We'll have a closer look at this on the next slide. Other than playing animations and blending between them, there are some other techniques like procedural animation or physics-based animation that help breathing life into our characters. We can directly control the joints or use some kinds of procedural animations to, for example, automatically make our character look at a given spot or place the hands or feet of the character using inverse kinematics based on the environment or some context. Physics-based animation can be used to, for example, create a falling character using ragdoll simulation, hair or cloth simulation, or jiggle of body parts. Blending is one of the key concepts in runtime animation, where each of the animations in the blending process gets a weight assigned between 0 and 1. This can basically be seen as how much influence a given motion has in the blending process. There are several types of blendings: transition blending, composition blending, and additive blending. Transition blending is used to create smooth transitions between animations. For example, between an idle animation and a walk. In this case, the influence or weight is increasing from 0 to 1 over a given transition period. Composition blending is used to compose a new animation based on multiple others. For example, a fast walk animation, which is a walk with a little bit of a run animation influence. It's using a bit of both motions. The influence or weight here is not changing over a period of time unless the player input specifies so, for example by moving the joystick. What happens internally? Both methods internally are the same thing. The weight value of the transition blending process is just animated over a given period of time, while for composition blending, it is mapped on some way to a parameter or an input device. The blend process itself is a linear interpolation of several skeletal poses for each frame. And in order to blend a pose, each component of the joint transform, as in position, rotation, and scale, are interpolated individually. Additive blending is an animation added on top of another one. This can be used to create recoil effects, for example, as you can see on the right. Here, the weight controls how much of the recoil additive animation is added on top of the walk animation. Let's have a look at what types of assets Emotion Effects uses and supports. On the top left, we have motions and motion sets. Each motion is an animation file created in a 3D application and imported via the FBX file format. Motion sets are collections of animations that we want to use for a given character. Motion sets are created and maintained inside the animation editor. And same goes for anim graphs. They contain the bits that form our controllable character based on the motions. We'll talk more about that on the next slides. Actor assets that you can see on the right contain the skeleton. And lastly, there's the mesh asset. Both the actor and mesh assets are imported via the FBX file format and created in 3D applications. And all of those assets together form our animated character in the middle. Anim graphs are the foundation of emotion effects. It is the concept on which most features are built upon. Anim graphs describe the behavior of a character using what you see is what you get tools. There should be no engineer needed. It is a way of describing how and when we want to blend between animations, forming a controllable character based on individual animation clips. A character can be in states. We can switch between them, and each state might be a composition of animations and other things controlling the skeleton. Anim graphs are composed of state machines and plant trees. A state machine provides a graphical way to break down the available parts of the character behavior. Actions like jumping or an attack, more complex moving variations, or just simple animations that should be automatically played in certain situations. They consist of states and transitions that are governed by conditions that control how and when we want to blade from one state to another. States could be, for example, a motion, a plant tree, or another child state machine. Basically, every node that can generate a skeletal pose without an input pose. The resulting pose of the anim graph of the currently active state will be applied onto the character. Transitions describe the possible path that we can go from one state to another. We can specify the duration of the blend from one state to another, the priority in case we have multiple, and we can also temporarily disable transitions in case you're testing a given area of the anim graph and don't want another transition to be triggered during that time. Conditions, the little traffic lights on the transitions, perform a number of checks. For example, if a speed parameter is above a given threshold, or a countdown that the transition won't be taken too fast after one another. The output of these checks determines whether the transition should be automatically activated or not. If the conditions evaluate true, the blending process will be started and the green line on the transition indicates that process. Most of the times, a state machine has one active state. Unless it's transitioning to another one, then two or even more might be active and evaluated. Plant trees are states inside state machines and are used for composition blending. They allow multiple animations to be blended smoothly together to different degrees. They might blend either parts of the skeleton together or the full one. We can define the degree of blending by incorporating parameters into the process. Processing and data flow is happening from left to right, ending up at the final node. The pose retrieved at the final node is forwarded and further processed at the parent state machine. Plant trees visualize the flow of pose data through a series of different nodes, each node contributing in some way to the final look of the pose or motion. And as you can see, not all nodes are active, and the execution flow is visualized by the highlighted connections. Let's create our first anim graph. We start off by creating a new motion state that we call idle, and we'll apply an idle animation onto it, which starts playing directly. Now let's add a new parameter that we call speed and a new plant tree that we'll use for locomotion. Now we'll use the speed parameter to indicate when we want to transition into the locomotion state and out of it. Let's add a parameter condition onto the transition. Select the speed parameter and test if the speed parameter is bigger than 0.2. And on the way back we do a similar thing, but we check if it's smaller than 0.2. If we increase the speed parameter, we're blending into the locomotion state. If I decrease it again, we blend back into the idle state. Now let's fill our locomotion state. We'll use two motion nodes. A walk animation and a run animation. We'll add a parameter node so that we have access to the speed parameter, and lastly a blend to node so that we can blend the walk with the run animation. Connect them all, connect the speed with the weight parameter, and now we can see the character walking. If I increase the speed, it's running. If I decrease it to 0, we transition back to the idle animation. There's still something weird going on, as we can see here with the feet. In those cases, it's good to start a recording. And then you can scrap through the situation and get a better understanding of what's happening. The issue that we were seeing just now was that our feet were sometimes flying in the air without touching the ground. Animation synchronization fixes this. Let's have a look at when this occurs and how we can fix it. In our case, the walk animation and the run animation start with the right foot followed by a left footstep. The durations of the two motions are different though. The run animation is shorter than the walk animation and thus loops faster. This results in the right foot hitting the ground earlier in the run animation than with the walk animation. Another issue might be that the user set different play speeds on the motion nodes, which alters the actual duration again, leading to the first issue. We now have the case where our animation footsteps are the same. What happens in case one animation has a right, a left, and a right footstep, while the other one only has a right and a left footstep? There's a special syncing mode for this that uses motion events that searches for the next footstep and syncs towards that rather than the full animation. Animation synchronization can be used when blending motions together. For example, when using blend 2, a blend end node, blend spaces, or state machine transitions. There's also situations where we don't want to synchronize our animations. For example, in the additive recoil animation that we showed earlier, or in the anim graph that we just created when going from the idle to the locomotion state. When syncing is enabled, there's a leading and a following animation. The leader provides the animation duration to use for the following animations, and the followers scale their animations to match the leading one. Internally, it's a two-step process. First, we sync our play speeds by interpolating play speeds based on the duration and the source play speeds. In our example on the right, the walk animation is longer than the run animation. Thus, we have to slow down the run animation to match their durations. After the durations are matched, we synchronize the play times. This is done by first retrieving the normalized play time from the leading animation, in our case the walk animation, and then apply the normalized play time to the following animation, in our case the run animation. We are back at our anim graph with the aim to fix the foot sliding issue. Let's first have a look at our animations. For the walk animation, we see that the right foot hits the ground early in the animation, followed by a left foot step. And at the end of the animation, the right foot newly touches the ground again. And the same goes for the run animation. The right foot hits the ground, followed by the left foot. And at the end, the right foot nearly touches the ground again. So that looks good. Let's go back to our anim graph. And increasing the speed parameter a little bit, we see that the issue is still present. In order to fix it, let's go to our blend 2 node, to a setting called sync mode, and set it to full clip based. After enabling it, we see that the play times are now matching. Things are looking good when changing the speed parameter. As a next step, let's introduce turns to our character. We're going to use blend spaces to extend our locomotion state with turns. Blend spaces allow parametric blending of animations based on a number of inputs. They basically enable animators to specify how the inputs are used to blend between multiple animations. We'll be looking at 2D blend spaces specifically. To make it a little bit less abstract, we already have a speed parameter in our anim graph, and we want to introduce a new one for turn speed. So now we have two input values, move speed and turn speed. And these two together form a Cartesian coordinate system, which is basically our blend space. Each input belongs to an axis. Move speed forms the horizontal axis and turn speed forms the vertical one. Now, each animation will be a point inside our blend space. In this example, we construct a blend space with a walk forward, a run forward, and a turn right animation. So, how do we construct our blend space? The base forms a set of input motions, And for each input motion, we want to calculate the motion coordinate. And there's two ways for this. Either we set it manually, or we use what we call an evaluator, which automatically extracts the motion coordinates based on some secondary motion features. And there are several available, like travel direction, slope, turn angle, travel distance, strafe velocity, and more. In our example, we want to use movement speed for the horizontal axis and turn speed for the vertical axis. Let's see how this looks like for our animations. The walk animation will turn into a point in the middle of the blend space. There's no turn speed involved, but there's a little bit of movement going on. The run animation has a higher velocity, and thus it's landing at a more right spot in the blend space. And our turn right animation has a little bit of forward velocity, but also a turn speed involved. Now that we have the motion coordinates for all of the animations, the last thing that we need to do is to calculate a triangulation. And this is done by Delaunay triangulation internally. Having that, our blend space is ready to be used. What happens at runtime? We have our two parameters, move speed and turn speed. Move speed, for example, might be 1 meter per second, and turn speed might be 20 degrees per second. Those two values together form a coordinate inside our blend space. And that's the coordinate that we want to evaluate the pose for. The first thing that we have to do is search the triangle in which our sample lies within. In our case, it's trivial because there's only one triangle, but the more animations are involved, the more triangles are generated. Now that we know the triangle, we also know the animations that are involved in the blending process, but we don't know the weights yet. We calculate the barycentric coordinates based on the input sample position and use those as weights for the blending process. Once we have the weights, we do a three-way blend. A three-way blend is basically we just sum up the local space transform components and take the weights into account. And this is how it looks like. Now that we know how blend spaces work, let's use them and change our locomotion state. Let's remove the input motions and the blend to node and replace it with a blend space node. Select the motions that we want to add in the blend space, which is all of the walk and run forward and turn animations. Select the move speed evaluator for the x-axis and the turn speed evaluator for the y-axis. Let's give it a test run. We see our foot sliding issues. Back in, let's enable motion syncing. Okay, that is looking good. In order to drive the blend space, we now need a new parameter for the turn speed. Let's first rename our speed parameter into move speed. And introduce a new one for turn speed. So we want to go left and right. Let's change the range from -1 to 1. Default it to going straight. Introduce two range remapper nodes. To go from the parameters inside the plan space, which are speed are from 0.49 to 5.79, and the turn speed is from minus 4.71 to 4.71. So we'll convert the move speed from a normalized value to 0.49, and the maximum speed was 5.79, and for turn speed we had an input value ranging from -1 to 1, and the use values on the x-axis in the plane space were minus 4.71 to 4.71. Now we're able to use the sliders from the parameters to make the character turn and walk. If we decrease it to 0, we're going back to the idle state. There is one last thing that I want to talk about before bringing our character into a level. Let's talk about motion extraction. Motion extraction is the process that, in case the animation is moving the character and thus moving the root joint along the space, takes the motion of the root node away from the root joint and applies it to the character capsule. In case of playing a walk animation, rather than resetting the character position back to the origin with each loop, motion extraction keeps the character smoothly walking forward. There are two ways to move your character around a level: game-driven root motion and animation-driven root motion. Game-driven root motion means that the animations are made in place. The root joint in this case stays at a static location and is not moving around in animation space. When playing an in-place animation in your game, your character might be walking, but it won't move around the level. You can see how an in-place animation looks like on the left. In game-driven root motion, you decide how fast the character or the player capsule is moving and reacting, and play the correct animations to match the speeds. For example, if your player capsule is moving forward at a decent speed, we play a walk animation. If it's moving a little faster, we increase the play speed of the walk animation, until we finally switch to a run animation. The downside is that the speed of the animations might not perfectly match the speed you're moving the character, and we might see some floating or foot sliding. Animation-driven root motion means that the animations determine how fast and far the character travels. The player capsule exactly moves the amount that the root joint moves in the animation. And this will perfectly match the distance covered and gets rid of the floating and foot sliding effects. The downside though is that the game cannot dictate the movements accordingly, and blendings from one animation to the other might introduce lags. So the trade-off here is fast reaction but some floating using game-driven root motion versus realistic but a little bit of lagging movement using animation-driven root motion. What happens internally? There is a motion extraction joint, which is basically projected to the ground plane version of the pelvis joint. And with each game tick, we calculate the change in this joint, as in a delta position and rotation around the up axis. And rather than letting the skeleton move away from the model space origin, we move the player capsule and compensate the inverse to the pelvis to make it stick at the model space origin. We call it motion extraction as it extracts the root motion from the animation and basically makes that an in-place one and apply that extracted trajectory delta onto the character capsule or game object. Let's have a look at how this is working in an anim graph, as we're not just dealing with single animations. Motion extraction originates at motion nodes. Trajectory deltas are calculated and output along with the resulting pose from the motion node. These deltas are then passed through the graph together with the pose and some other data, from the left to the right, towards the final node in a plan tree, and then upwards the hierarchy up to the root state machine. The motion extraction or trajectory deltas can be blended together. When blending a walk with a run animation, for example, we need to blend these deltas together as well, to not introduce the floating effect by the blending process again. First, both deltas are extracted and kept in memory, and when they both reach a blend node, the delta position and rotation are blended together and the resulting delta is then used for the next node input. And the same thing happens when transitioning from one state to the other. There might be some situations where we don't want to blend the trajectory deltas and just use the one from the source or the target motion. For example, we can directly use the target deltas in case we want to change the movement of the character fastly, while we still blend towards our new animation. This introduces the same downsides as we talked about in game-driven root motion though. But here, we can control how and when we want to use it, in cases when reaction time is more important than a realistic look. We are back at the editor, where we want to add our character and make it controllable. Let's start off by adding a new entity for our character. And add an actor component to it, and an anim graph component. Select the assets. And place it in front of the camera. When going into game mode, we see that the character is in the idle state and playing the idle animation already. Now we want to control those two parameters so that the character will start moving and turning. We do that by adding an input component and creating a new input bindings for it. Let's create a new event for move speed. Add an event generator for it. We want to use the y-axis for the move speed. And the x-axis for the turn speed. Let's save the input bindings. And select the asset again. And the last thing that we need now is a script canvas graph that connects the input bindings and sets the parameters of the anim graph. To do that, we add another component, script canvas component, and create a new graph. We start off by an onEntity activated node. And then two input handlers. One for move speed. And the other one for turn speed. Get them activated when the entity is activated. And those should then control a set named parameter. Float node. And the parameter that we want to control is also named move speed. We do the same thing for turn speed. Save the graph. Go into game mode and we should be able to control our character already. Okay, that is working. Now we can attach the camera to the character and move along with the character. Thanks for watching. Please join our Discord channel. I'm happy to talk more about the O3DE animation system or how we can shape the future of animation technology together. Hope to see you there.